I'm Preeti Rajendran, Marketing Engineer with the Sensor Signal Path product line at Texas Instruments. TI recently announced the world's first inductance to digital converter, the LDC1000. In this video, I'm going to take you through the LDC1000 EVM, how to get jump-started on your design with the GUI, some key parameters that you would need to keep in mind and what they mean, and then finally give you a short demo of using the LDC1000 EVM in a simple distance sensing application. To get right into it, the LDC1000 EVM is displayed here. Due to the small form factor, I'm going to take you to a larger image to show you the three different sections of this EVM. The first section has the PCB sensor coil along with a tiny capacitor. The second section has the LDC1000 IC. The third section is simply a USB interface using the MSP430. This EVM is uniquely designed to give you as much flexibility in your design as possible. So each section can be separated by just snapping a portion off. The sensor coil can be snapped off, and you can use your own customized coil for your specific application. The LDC IC itself can be snapped off, and you can interface the LDC to an existing microcontroller in your system. Alternatively, you could also use combinations of the LDC and coil to design a multi-channel system interfacing to your microcontroller. To give you an idea of what this system looks like, we have the coil connected to a capacitor, which interfaces with the LDC. This is essentially an LC tank that is created here. As a conductive object moves further or closer to the coil, it changes the characteristics of the coil. The coil can be modeled as an inductor in series with a parallel resistor. The resistor here is marked RS as a parasitic series resistance, and the L is also variable. These two vary based on how close or far away you're moving your conductive target. To go a step further, you could model the RS as RP. RP being a parallel parasitic resistance as a Norton equivalent circuit of the system. Now, RP can be derived using this simple equation here. But similarly, as you move your object closer or farther away from the coil, not only are you changing the inductance, you're also changing RP. The LDC is very sensitive to changes in L and RP, and different applications have different ranges for this resonance impedance. This is important to keep in mind as you set up your system and set up the RP min and RP max register settings. The LDC has two key outputs. The first one is 1 over RP. This is in 16-bit resolution, and you can derive the actual value of RP of the sensor coil from this data. The second one is the resonant frequency. This is given in 24-bit resolution, and using the formula on the screen, you can derive the actual inductance of your sensor coil. The unique combination of L and RP from this system can really expand the number of applications that you can use this technology in, all the way from position or motion sensing, or even getting into metal composition detection. On the GUI, when you first open it up, I'd like to go over some default parameters and why they're there. The coil that's mounted on the EVM is a 15mm diameter coil with 2 layers. The LC tank is tuned to a 3.6 megahertz frequency, with the inductance of the coil when no target is present is around 19 microhenry, and the capacitor value that's chosen accordingly is 100 picofarad. The sensor's RP range is 4 kiloohms to 20 kiloohms. In order to make sure that when doing any sort of measurement that we capture the entire range, the default values that you will see on this GUI for RP min and RP max are around 2 kiloohms to about 38 kiloohms. When you change out the coil in your system, you need to make sure that you calculate RP min and RP max accordingly. The detailed calculations can be found in the LDC1000 datasheet. As we move into the GUI, the top left part of the GUI is where we have the sensor capacitor value. By default is 100 picofarads as in the EVM. The graph on the left is indicative of the RP value, and the graph on the right is indicative of the inductance value. The easiest way to demo this is to show you the LDC1000 EVM in action. We have a metal target that is fixed to this mount. The mount will be moved using the stepper motor that's down here. For the purpose of the demo, we snapped off the coil and put it on this mount so that it's parallel to the metal plate. The EVM is connected to the GUI, and you will see the LDC response on the screen. Once we start the motor and move the target towards the coil, you will see the gradual change in RP as well as in L. To get more details behind how these graphs are formed, again, please refer to the datasheet. I hope that in this video you had a better understanding of getting started with your LDC1000 EVM. For more information on TI's inductive sensing technology and getting an EVM of your own, please visit ti.com/LDC. Thank you very much.